About 4.6 billion years ago, Earth was a very different world. There were no people, no cities, and no written history to record the weather. Instead, the planet experienced endless changes that shaped everything we see today. Giant ice ages froze huge parts of the world, while long periods of intense heat covered the land with thick forests and vast deserts. Powerful storms, changing oceans, and shifting continents transformed the planet again and again. Scientists have spent many years trying to understand what Earth's climate was like at different times in the distant past. They know that the world has never stayed the same for very long. Temperatures have risen and fallen many times. Some places that are now dry deserts were once covered by shallow seas. Areas that are now filled with thick forests were once frozen under huge sheets of ice. There were also times when warm tropical plants grew close to places that are now cold for most of the year. Since no people were alive to record these changes, scientists have had to search for natural evidence that has survived through time. Every discovery adds another piece to the story of Earth's changing climate and helps explain how the planet has changed over millions of years. The evidence scientists study is found almost everywhere. It is hidden inside rocks, trapped beneath thick layers of ice, locked inside ancient caves, buried deep below the ocean floor, and preserved inside the remains of plants and animals. None of these natural records can speak with words, yet each one contains information about the weather and climate that existed when it formed. Scientists carefully collect these clues, study them in laboratories, and combine the results to build a detailed picture of Earth's past. This work requires patience because every clue must be tested many times before it becomes part of the scientific record. One of the most important places scientists look is inside layers of rock. Rocks form over very long periods, and each layer can preserve information about the environment that existed at the time it was created. As sand, mud, tiny shells and other materials settle on the ground or at the bottom of lakes and oceans, they slowly build new layers. Over many thousands and millions of years, these layers become solid rock. The oldest layers usually lie beneath the younger ones, creating a record that stretches back through time. By studying these layers carefully, scientists can work out the order in which different events happened. The color of a rock can provide valuable information about ancient climates. Deep red rocks often suggest that they formed under warm conditions, where oxygen was common. Dark rocks may show that they formed in water with very little oxygen. White rocks made from minerals that form as water dries up can point to hot and dry climates, where lakes or shallow seas slowly disappeared. Each color offers another clue that helps scientists understand the conditions that existed when the rock formed. The size of the grains inside a rock is also important. Large stones and coarse sand usually mean that strong rivers, powerful waves, or fast-moving water carried the material before it settled. Very fine mud often shows that the water was calm and slow. By measuring these grains and studying how they are arranged, scientists can learn about ancient rivers, coastlines, lakes, and oceans. These details also reveal how rainfall and weather changed over time. Some rocks preserve tiny cracks that formed when wet mud dried in the sun. These dried mud cracks show that the ground was once exposed to air, before it became buried by new layers of sediment. Scientists use these patterns to identify places that experience dry seasons or changing water levels. In other locations, rocks contain marks left behind by ancient raindrops. Although these marks are rare, they provide direct evidence that rain once fell on the surface before the mud hardened into stone. Scientists also study ripple marks preserved in rocks. These small wave-shaped patterns were created by moving water or wind. The shape and direction of the ripples helps scientists understand whether the area was once covered by a river, a lake, a beach, or shallow seawater. Even after millions of years, these delicate patterns can remain almost unchanged inside solid rock. Another important source of information comes from fossils. Fossils are the preserved remains or traces of ancient living things. Plants, animals, shells, pollen, and even tiny microscopic organisms can all become fossils under the right conditions. Every living thing needs certain environmental conditions to survive. Because of this, the fossils found in a rock often reveal what the climate was like when those organisms were alive. Plant fossils are especially useful for understanding ancient climates. Different plants grow best under different conditions. Some need warm temperatures and heavy rainfall throughout the year. Others survive in cool regions or dry environments. When scientists discover fossil leaves, wood, seeds, or pollen, they compare them with modern plants. This helps them estimate the temperatures and rainfall that existed when those ancient plants were growing. Leaves can reveal even more details. Large leaves with smooth edges are often linked to warm and wet climates. Smaller leaves with different shapes may point to cooler or drier conditions. Scientists measure thousands of fossil leaves from many different locations. They use these measurements together with information from living plants to estimate ancient temperatures with surprising accuracy. Pollen grains are another valuable source of evidence. Every flowering plant produces pollen, and these tiny grains are protected by an extremely tough outer covering. Because of this strong coating, pollen can survive for very long periods after the plant itself has disappeared. Lakes, swamps, and wetlands often collect layer after layer of pollen every year. Scientists remove long tubes of sediment from these places and examine the pollen trapped inside each layer. Changes in the kinds of pollen show how forests, grasslands, and other types of plant life changed through time. Trees also preserve climate information inside their trunks. Every year, many trees produce a new growth ring. In years with good growing conditions, the rings become wider. During dry or cold years, the rings remain narrow. Scientists study living trees as well as preserved ancient wood to build long records of changing weather. By matching ring patterns from different trees, they can create climate records that stretch back many thousands of years in some regions. These records help scientists understand periods of drought, heavy rainfall, and changing temperatures. Animal fossils also provide important evidence. The presence of certain animals tells scientists about the environment in which they lived. Fossils of animals that lived only in warm seas show that those waters were once much warmer than they are today. Fossils of animals adapted to cold conditions indicate cooler climates. Even tiny marine organisms preserved in ocean sediments reveal valuable information because different species prefer different water temperatures. Shells from ancient sea creatures are especially useful. As these animals grew, they built their shells using minerals taken from seawater. The chemical makeup of these shells changes slightly depending on the temperature of the water in which they lived. Scientists measure these tiny chemical differences using highly sensitive laboratory equipment. These measurements allow them to estimate the temperatures of ancient oceans that existed millions of years ago. Tiny organisms called foraminifera have become some of the most valuable climate records ever discovered. These single-celled creatures live in oceans all over the world and produce small shells. When they die, their shells sink to the seafloor, where they become part of thick layers of sediment. Scientists drill deep into the ocean floor to collect long cylinders of these sediments. Each layer contains countless microscopic shells that formed under different climate conditions. By studying them one layer after another, researchers build detailed records of changing ocean temperatures extending back millions of years. Coral reefs also record climate history. Corals grow slowly by adding thin layers to their hard skeletons every year. These layers preserve chemical information about sea temperature and the chemistry of ocean water. Scientists carefully cut thin sections from fossil corals and study their growth patterns under microscopes. This work helps reveal changes in tropical oceans over many thousands of years and continues into the present day. Earth was formed about 4,500,000,000 years ago during the early history of the solar system. At that time, the young planet was a very different place from the world that exists today. There were no oceans, no rivers, no clouds, no plants, no animals, and no people. The surface was extremely hot because the planet had only recently formed from countless pieces of rock and metal that crashed together over a long period. Every major collision released an enormous amount of heat. Radioactive elements inside the young Earth also produced heat as they slowly broke down. This kept much of the inside of the planet in a melted state and left the surface far too hot for liquid water to remain. During this early period, Earth did not have the kind of atmosphere that surrounds the planet today. The air that people breathe now is made mostly of nitrogen and oxygen. But these gases were not present in the same amounts during Earth's earliest years. The first atmosphere was very different. Scientists believed that the earliest atmosphere was made mostly of very light gases, such as hydrogen and helium. These gases were common throughout the young solar system because they had formed soon after the universe itself came into existence. As Earth grew larger, its gravity pulled in some of these gases from the cloud of material surrounding the young sun. Even though Earth was able to gather hydrogen and helium, this first atmosphere did not remain around the planet for very long. Earth was still extremely hot, and the sun was much more active than it is today. The young sun released powerful streams of charged particles into space. These streams are known as the solar wind. Because Earth did not yet have a strong magnetic field to protect it, much of the light, hydrogen and helium escaped into space. The heat of the young planet also gave these light gases enough energy to rise high above the atmosphere, where they were lost forever. As a result, the first atmosphere slowly disappeared. After the loss of the earliest atmosphere, Earth continued to change. Inside the planet, heavy materials such as iron and nickel moved toward the center. Lighter rocks rose closer to the surface. This movement created different layers inside Earth. The center became a metal core, while the outer parts formed the mantle and the crust. Even though a thin crust slowly began to form, the inside of the planet remained very hot. Large amounts of melted rock continued to move beneath the surface. As this melted rock moved upward, it reached the surface through countless volcanoes. The young Earth was covered with volcanic activity. Some volcanoes erupted quietly, while others exploded with great force. They released huge amounts of gas into the air. This process happened again and again over millions of years. Instead of producing only lava, these volcanoes also released gases that had been trapped deep inside the planet since its formation. The gases released by these volcanoes slowly created a second atmosphere. This atmosphere was very different from the first one. Instead of being filled mostly with hydrogen and helium, it contained large amounts of water vapor, carbon dioxide, nitrogen, sulfur gases, carbon monoxide, methane, ammonia, and several other gases in smaller amounts. There was almost no free oxygen. This meant that no humans or animals could have survived in this environment. Water vapor became one of the most important gases released by volcanic eruptions. Every eruption added more water vapor to the atmosphere. Since the surface was still extremely hot, this water remained as gas instead of becoming liquid. Thick clouds of water vapor covered much of the sky, but the heat prevented lasting rainfall from reaching the ground. Any rain that did fall quickly turned back into vapor because the surface remained hot enough to boil water almost immediately. Carbon dioxide also became one of the major gases in the atmosphere. Volcanoes released enormous amounts of it over a very long time. Carbon dioxide trapped heat in the atmosphere, helping to keep the young Earth warm. Nitrogen also became more common. Unlike many other gases, nitrogen is not easily changed by chemical reactions under ordinary conditions. Because of this, it slowly built up in the atmosphere over time. Today, nitrogen is still the most common gas in Earth's atmosphere. The atmosphere during these early years was thick, cloudy, and filled with gases from volcanic eruptions. The sky probably did not look blue as it does today. Thick clouds, volcanic dust, and floating particles likely gave the sky a dark appearance for long periods. Sunlight had difficulty reaching the surface because so much material was present in the atmosphere. Ash from volcanic eruptions spread through the air while gases mixed together high above the ground. The surface itself continued to change. Large areas were covered with flowing lava. New crust formed as melted rock cooled. At the same time, fresh lava broke through older rock, destroying parts of the crust and creating new land again and again. Earth was still settling into the stable planet that would appear much later. As the planet slowly lost heat to space, temperatures gradually began to fall. This cooling happened very slowly over millions of years. The crust became thicker and stronger in many places. Although volcanic eruptions continued, more solid rock remained on the surface for longer periods. The lower temperatures allowed changes to begin taking place in the atmosphere. Water vapor that had filled the sky for a very long time slowly cooled. As it cooled, it changed into tiny drops of liquid water. These drops gathered together to form thick clouds. At first, the heat from the surface caused much of this water to return to vapor. As cooling continued, however, more of the water remained in liquid form. Clouds became larger and heavier. Eventually, the atmosphere reached conditions where rain could survive the journey from the clouds to the ground. This marked one of the most important moments in Earth's early history. Rain began falling onto the hot surface. Scientists believed that this rainfall lasted for an extremely long time. Instead of lasting only a few days or weeks, rain may have continued for thousands or even millions of years, as the atmosphere released the enormous amount of water vapor it contained. The first rain fell onto land that was still warm from Earth's early heat. In many places, the water quickly turned back into vapor after reaching the ground. In cooler areas, some of the water remained. As temperatures continued to fall, larger amounts of rain collected instead of disappearing. Small pools of water formed in low places across the surface. These pools slowly grew larger as more rain continued to fall. Rainwater also flowed across the rocky ground. It carried tiny pieces of rock and minerals with it. Water entered cracks in the surface and slowly changed the shape of the land. Hot rocks broke apart more easily as water reached them. Chemical reactions between water and minerals began changing the surface in many different ways. The first flowing water created the earliest streams. As rainfall continued, streams joined together to form larger channels. Water naturally moved downhill into lower areas. Over time, large basins collected more and more water. These growing bodies of water eventually became the earliest oceans. The first oceans were not exactly like today's oceans. They were much hotter and contained different amounts of dissolved minerals and gases. Water mixed with chemicals released from volcanic activity. Hot springs beneath the oceans added even more minerals. The seawater slowly changed as chemical reactions continued over long periods. Some of Earth's water may also have come from objects that struck the young planet. During the early history of the solar system, many icy bodies traveled through space. Some scientists believe that these objects delivered additional water when they crashed into Earth. Other scientists believe that most of Earth's water came from inside the planet through volcanic activity. Many researchers think that both sources probably played a part in supplying the water that eventually filled the oceans. As oceans spread across Earth's surface, they became an important part of the planet's changing climate. Water stored heat and slowly released it back into the atmosphere. Water also continued to evaporate into the air. As the sun warmed the ocean surface, water changed back into vapor and rose into the atmosphere once again. This vapor formed new clouds. The clouds later produced more rain. This ongoing movement of water became the beginning of Earth's water cycle, although it continued changing as the planet itself continued to develop. The appearance of large oceans also changed the atmosphere. Carbon dioxide from the air dissolved into seawater. Some of it reacted with minerals and became trapped inside rocks forming beneath the oceans. This slowly reduced the amount of carbon dioxide in the atmosphere. These changes took place over extremely long periods and continued as Earth's surface kept evolving. The birth of weather was closely connected to these changes. Weather depends on an atmosphere, heat, and moving air. Once Earth had a thick atmosphere and temperatures began to vary from place to place, air started moving across the planet. Warm air rose while cooler air moved into its place. These movements created the first winds. These early winds were not exactly like modern winds, because Earth's atmosphere was still changing. The gases were different. Temperatures remained much higher in many regions, and volcanic eruptions continued releasing fresh material into the air. Even so, moving air became an important part of the young planet. Winds carried water vapor, volcanic ash, dust, and gases from one place to another. They also helped shape the developing weather patterns that continued changing as Earth slowly cooled. When Earth was still a very young planet, it was a place filled with intense heat. The surface looked nothing like the world that exists today. There were no forests, no rivers flowing across wide landscapes, no grasslands, and no animals. The planet was still forming after countless pieces of rock, metal, dust, and ice had come together under the pull of gravity. Every new impact released a huge amount of energy. Each collision added even more heat to a world that was already extremely hot. Instead of a calm surface covered with solid ground, much of the young planet was made of melted rock. Large areas remained liquid for long periods because there was far more heat being produced than could escape into space. One of the biggest reasons for this extreme heat was the way Earth formed. During the birth of the solar system, countless objects moved around the young sun. Many of these objects crashed into one another. Some broke apart, while others joined together and grew larger. Earth slowly became one of the largest rocky bodies in this growing family of planets. Every collision turned movement into heat. The larger Earth became, the stronger its gravity became. stronger gravity pulled in even more objects, creating even more impacts. Every impact added fresh energy to the growing planet, keeping temperatures at very high levels. As Earth continued growing, heavy materials such as iron and nickel slowly moved toward the center. This process released even more heat. The movement of these heavy elements through the melted rock created powerful energy deep inside the planet. Lighter rocks stayed closer to the surface while heavier materials sank lower. This separation helped create Earth's core, mantle, and early crust. The process did not happen in a short time. It continued while the planet remained extremely hot inside and outside. Another important source of heat came from radioactive elements trapped inside Earth. Some natural elements slowly changed into other elements through radioactive decay. Every small change released tiny amounts of heat. Even though each event released only a little energy, countless atoms were changing all the time. Together, they produced enough heat to help keep the inside of the planet very hot. Some radioactive elements that were more common during Earth's earliest history released energy faster than many of those that remain today. This helped maintain high temperatures for a very long time. The young sun also played a part in shaping early Earth. Although it did not shine as brightly as it does now, its energy still reached the young planet. The atmosphere that surrounded Earth trapped much of the heat near the surface. Instead of allowing warmth to escape easily into space, certain gases held on to that heat. This made the surface warmer than it would have been if those gases had been absent. The first atmosphere was very different from the air people breathe today. There was almost no free oxygen. Instead, the atmosphere contained large amounts of water vapor, carbon dioxide, methane, ammonia, sulfur gases, and other gases released by volcanoes. Many of these gases came directly from Earth's interior. As melted rock reached the surface and cooled, gases that had been trapped underground escaped into the atmosphere. This process continued over millions of years and slowly built a thick blanket of gases around the planet. Volcanic activity was one of the most common events during this early time. Volcanoes were active across many parts of the young planet. Melted rock rose from deep inside Earth and poured across the surface. Some eruptions happened through mountain-shaped volcanoes, while others burst from long cracks in the ground. Thick streams of lava spread across large areas before slowly cooling into solid rock. New eruptions often covered older rocks, creating layer after layer over long periods. The inside of Earth remained much hotter than it is today. Heat constantly moved upward from deep within the planet. This caused melted rock to rise while cooler rock slowly sank. These movements helped shape the early crust. The crust itself was thinner and less stable than it is now. In many places it cracked, broke apart, and melted again. New rock formed while older rock disappeared beneath the surface. This cycle happened again and again because of the enormous amount of heat stored inside the young planet. Earth's surface rarely remained quiet for long. Earthquakes shook the ground as large pieces of the crust shifted. Cracks opened across wide regions. Fresh lava rose through these openings and spread over the land. Gases escaped from underground through volcanic vents, adding more material to the atmosphere. Steam, carbon dioxide, sulfur dioxide, hydrogen, and other gases poured into the sky almost without interruption. Water existed during this period, but much of it remained as water vapor because temperatures near the surface were still extremely high. Thick clouds filled the atmosphere. Steam rose from volcanic areas and from hot surfaces, where liquid water could not remain for long. As Earth slowly lost heat over time, some of this water vapor began changing into liquid water. Heavy rain fell again and again. Some scientists believe that rain continued for very long periods as the atmosphere slowly cooled enough to allow water to remain on the surface. The first oceans formed as rainwater collected in low places across Earth's surface. Water also came from ice-rich objects that struck the young planet during its early history. As temperatures slowly dropped in some regions, more water stayed in liquid form instead of returning to the atmosphere as steam. These early oceans were much warmer than the oceans people know today. Heat from below continued warming the water, while volcanoes released fresh gases into the air above. The atmosphere continued changing as volcanic activity released new gases. Carbon dioxide became one of the most important gases because it trapped heat very effectively. Methane also helped keep temperatures high. Water vapor added even more warming because it is one of the strongest natural greenhouse gases. Together, these gases created greenhouse conditions that kept much of Earth's heat close to the surface. A greenhouse effect happens when certain gases allow sunlight to reach the ground, but slow the escape of heat back into space. On early Earth, this natural process was much stronger because greenhouse gases were present in much larger amounts than they are today. Heat remained trapped for longer periods, making it difficult for the planet to cool quickly. This helped explain why Earth stayed hot even as some energy escaped into space. Carbon dioxide entered the atmosphere mainly through volcanic eruptions. Every eruption released more gas from deep inside the planet. Since there were no forests, grasslands, or large living systems to remove carbon dioxide from the air, much of it remained in the atmosphere. Later, as oceans grew larger and simple forms of life appeared, some carbon dioxide slowly became stored in rocks and seawater. During Earth's earliest history, however, this process had only just begun. Methane also played an important role. It came from volcanic activity and from chemical reactions taking place beneath Earth's surface. Later, tiny living organisms also began producing methane. This gas was especially effective at trapping heat, helping maintain warm conditions across the planet. Sulfur gases released by volcanoes affected the atmosphere in several ways. Some formed tiny particles high in the air. These particles interacted with sunlight and influenced temperatures in different ways depending on the conditions. They also became part of chemical reactions taking place in the atmosphere. The early atmosphere was far more chemically active than the one people experience today. Lightning frequently flashed through thick clouds filled with volcanic gases, steam, and ash. Strong storms developed as heat caused air to rise rapidly. Hot air carried water vapor high into the atmosphere where cooling allowed clouds to form. These storms produced heavy rainfall and powerful winds. Rainwater flowed across newly formed rock, slowly wearing it down and carrying minerals into the growing oceans. The young oceans contained many dissolved minerals washed from fresh volcanic rocks. Hot water flowing through cracks beneath the ocean floor also carried minerals into seawater. In many places, seawater entered deep cracks, became heated by nearby melted rock and returned to the ocean, carrying dissolved chemicals. These underwater systems remained active because Earth's interior continued supplying enormous amounts of heat. The sky during this time probably looked very different from today's sky. Thick clouds often covered large areas. Volcanic ash sometimes filled the air after major eruptions. Sunlight reaching the surface could change from day to day depending on volcanic activity and cloud cover. The atmosphere itself contained gases that no longer exist in such large amounts. Large impacts from space continued after Earth first formed. Although they became less common over time, many large rocks still struck the planet. Each impact released fresh heat, created huge craters, and sometimes melted nearby rocks. The largest impacts could throw enormous amounts of dust and melted material into the atmosphere. Some impacts even caused parts of Earth's surface to melt again. These impacts also influenced volcanic activity. Powerful collisions created cracks deep inside the crust. Melted rock could move through these weak areas more easily, leading to fresh eruptions. The combined effects of impacts and volcanic activity kept Earth's surface changing almost constantly. The continents known today did not yet exist in their present form. Instead, small pieces of early crust formed, broke apart, melted, and formed again. Some pieces survived long enough to become the oldest parts of today's continents. Many of these ancient rocks have been changed by heat and pressure over billions of years, but they still provide valuable information about Earth's earliest history. Scientists study these very old rocks to understand how hot the young planet was. Certain minerals can survive for extremely long periods. By examining their chemical makeup, researchers can estimate the temperatures at which they formed. These ancient minerals provide important clues about conditions during Earth's earliest history. Some crystals formed while melted rock cooled slowly deep underground. Others formed near the surface where volcanic activity was common. Their chemical records help scientists build a picture of a world shaped by intense heat, powerful volcanic activity, and a thick atmosphere filled with greenhouse gases. The heat inside Earth also drove the slow movement of material beneath the surface. Hot rock expanded, became less dense, and rose upward. As it reached shallower depths, it cooled and slowly moved sideways before sinking again. These movements continued over very long periods and supplied fresh melted rock to volcanic regions. This constant recycling helped shape the surface throughout Earth's early history. The first great ice ages in Earth's history were among the most important climate events that ever happened on the planet. These freezing periods lasted for very long stretches of time and changed the land, the oceans, the atmosphere, and the living things that existed during those distant ages. Scientists have spent many years studying rocks, ancient sediments, tiny fossils, and chemical signs preserved inside minerals to understand how these cold periods developed and how they affected life. Evidence collected from many parts of the world shows that Earth experienced several major ice ages during its long history. Among the most remarkable of these were the snowball Earth events, when huge ice sheets may have spread across almost the entire surface of the planet. These events happened so long ago that no direct record remains, but the rocks left behind provide valuable clues about what took place. Earth was not always warm. Its climate has changed many times since the planet formed. Some periods were much hotter than today, while others were much colder. These changes did not happen overnight. They took place over millions of years because of many natural processes working together. The position of the continents changed as they slowly moved across the surface of the planet. Volcanoes released gases into the atmosphere. Rain removed some gases from the air by helping rocks break down. The sun itself slowly became brighter over time. Changes in Earth's orbit and its tilt also affected the amount of sunlight reaching different parts of the world. All of these factors helped shape Earth's climate across its long history. The snowball Earth events happened during a period known as the Neoproterozoic era. This era began about 1 billion years ago and ended about 538 million years ago. During this long span of time, Earth experienced several major climate changes. Scientists believe that at least 2 of these freezing events were especially severe. These are known as the Sturtian glaciation and the Marinoan glaciation. The Sturtian glaciation began about 717 million years ago and lasted for around 57 million years. The Marinoan glaciation happened later, beginning about 650 million years ago and ending around 635 million years ago. Some scientists also discuss another possible freezing event called the glaciers glaciation, which occurred about 580 million years ago, although it appears to have been less severe than the earlier events. Before these freezing periods began, Earth looked very different from the modern world. The continents were arranged in different positions because they had been slowly drifting across the planet for hundreds of millions of years. Large landmasses lay near the equator instead of near the poles. This arrangement may have played an important role in changing the climate. Warm temperatures and heavy rainfall near the equator caused large amounts of rock to break down. This process is known as weathering. As rocks broke apart, they removed carbon dioxide from the atmosphere. Carbon dioxide is one of the gases that helps keep Earth warm by trapping heat. When large amounts of this gas were removed from the air, the atmosphere slowly became less able to hold warmth. This gradual loss of carbon dioxide may have caused global temperatures to fall little by little. As temperatures dropped, snow and ice began spreading farther away. From the poles, ice reflects much of the sunlight that reaches it. Land and oceans without ice absorb much more sunlight. As more ice covered Earth's surface, even more sunlight was reflected back into space instead of warming the planet. This caused temperatures to fall even further. The growing ice created even colder conditions, allowing still more snow and ice to spread. Scientists believe this process may have continued until ice reached areas very close to the equator. This process is known as the ice albedo feedback. The word albedo refers to how much sunlight a surface reflects. Bright surfaces such as snow reflect a great deal of sunlight, while dark surfaces such as open oceans absorb much more. As ice spread across larger parts of Earth, more sunlight was reflected into space. Less heat remained on the planet. The colder temperatures allowed even more ice to form. This cycle may have continued for a very long time, leading to one of the coldest periods in Earth's history. Scientists continue to debate exactly how much of Earth's surface became frozen during these events. Some researchers believe that almost the entire planet became covered with thick ice, from the poles to regions very close to the equator. Others suggest that small areas of open water may have remained, especially in certain tropical regions. Even if some open water existed, the planet would still have been far colder than almost any other time in Earth's history. Huge glaciers likely covered much of the land, while thick sea ice spread across vast areas of the oceans. Evidence supporting these ancient ice ages comes from many different kinds of rocks found around the world. One important clue comes from glacial deposits. Modern glaciers leave behind mixtures of rocks, sand, mud, and gravel as they move. Ancient glaciers did the same thing. These deposits, called tillites, have been discovered on several continents. Their characteristics closely match materials left by glaciers today. This suggests that powerful glaciers once moved across those ancient landscapes. Another important clue comes from rocks that contain scratches made by moving ice. When glaciers slowly move across the land, rocks trapped beneath the ice scrape against the ground. These movements leave long marks on the underlying rock surface. Scientists have found many of these ancient scratches preserved in rocks that formed during the Neoproterozoic era. Their presence shows that glaciers once passed over those regions. One of the strongest pieces of evidence comes from the location of these ancient glacial rocks. Scientists can determine where continents were located millions of years ago by studying tiny magnetic minerals inside rocks. These minerals record the direction of Earth's magnetic field at the time the rocks formed. By measuring these ancient magnetic directions, researchers discovered that some glacial deposits formed in regions that were once located close to the equator. Today, glaciers rarely form near the equator because temperatures are generally too warm. Finding ancient glacial rocks from tropical regions suggests that Earth was much colder during those times. Scientists also study layers of rock known as cap carbonates. These unusual rocks are found directly above glacial deposits in many places around the world. They formed after the glaciers disappeared. Their chemical makeup suggests that they were created when very large amounts of carbon dioxide entered the atmosphere and later dissolved into the oceans. This supports the idea that volcanic activity continued throughout the freezing period while weathering nearly stopped, because thick ice covered much of the land. As volcanoes kept releasing carbon dioxide, the gas slowly built up in the atmosphere over millions of years. Eventually, carbon dioxide levels may have become extremely high. Since carbon dioxide traps heat, the growing amount in the atmosphere slowly increased global temperatures. Once temperatures rose enough for melting to begin, ice started disappearing. As the bright ice vanished, darker land and ocean surfaces became exposed. These darker surfaces absorbed much more sunlight. This increased warming even further. The melting spread across the planet until the long freezing period finally ended. Scientists estimate that carbon dioxide concentrations during the end of a snowball Earth event may have become many times higher than modern levels. Such high concentrations could have created powerful warming after millions of years of volcanic gas release. Once the ice retreated, Earth may have experienced a period of unusually warm temperatures before the climate gradually stabilized again. The oceans during these freezing periods were very different from today's oceans. Thick sea ice covered large areas of the surface. Sunlight could not easily reach the water beneath the ice. Since sunlight is necessary for many kinds of microscopic organisms that perform photosynthesis, life in the upper ocean faced serious challenges. Many living things depended directly or indirectly on these tiny organisms for food. Scientists believe that some areas beneath thinner ice may still have received enough sunlight for photosynthesis to continue. Cracks in the ice, places where volcanoes warmed nearby waters, and regions with seasonal melting may also have allowed some sunlight to reach the water. These areas could have served as places where living organisms survived while much of the planet remained frozen. Deep ocean environments may also have provided safe places for certain forms of life. Hydrothermal vents on the ocean floor release hot water rich in minerals. These environments support living communities that do not depend on sunlight. Instead, bacteria obtain energy from chemical reactions involving minerals released from Earth's interior. Similar communities exist today around hydrothermal vents. Scientists think such environments may have helped some organisms survive during the snowball Earth events. Small bodies of liquid water beneath the ice may have existed in certain places. Geothermal heat from Earth's interior continued warming the ground below glaciers. In some locations, this heat may have melted ice from below, creating hidden lakes beneath thick ice sheets. Similar lakes exist today beneath the Antarctic ice sheet. Although conditions were extremely cold, these hidden waters may have supported simple forms of life. Volcanic regions also remained active during these freezing ages. Volcanoes continued erupting through the ice and beneath the oceans. Lava flowing beneath glaciers could melt surrounding ice, creating temporary pools of water. Volcanic islands may have remained partly free of ice in some locations because of heat from Earth's interior. These areas could have offered additional places where organisms survived. The atmosphere during these freezing periods probably contained less water vapor than during warmer times because cold air holds less moisture. Snow still fell in many places, adding new layers to the growing ice sheets. Strong winds moved snow across frozen landscapes. Dust from exposed volcanic ash and dry regions may have settled onto the ice surface in some places. Seasonal changes still occurred because Earth's orbit around the Sun continued as usual, although temperatures remained extremely low. The thickness of the ice remains uncertain. Some scientists suggest that sea ice may have reached hundreds of meters thick in certain regions. Land glaciers may have become even thicker as snow accumulated year after year over millions of years. These massive ice sheets slowly flowed across the land under their own weight, reshaping mountains, valleys and plains wherever they moved. As glaciers advanced, they ground rocks into fine particles. These materials were carried along by the moving ice. When melting finally began, enormous amounts of sediment were transported into rivers and oceans. This changed coastlines, created new sediment layers, and affected ocean chemistry for a long time after the ice ages ended. Life during the Neoproterozoic era was much simpler than the plants and animals that exist today. There were no forests, birds, mammals, flowering plants, or dinosaurs. The oceans contained microscopic organisms, algae, bacteria, and some early multicellular life. Although these organisms were small, they formed the foundation of Earth's living systems. Their survival through these severe freezing events became important for everything that followed in later ages. Many bacteria possess remarkable abilities to survive difficult conditions. Some can become inactive for long periods when their environment becomes unfavorable. Others live beneath rocks, inside tiny cracks, or deep below the surface where temperatures remain more stable. These abilities may have allowed many bacterial groups to survive the long frozen periods. Algae also faced difficult conditions because they require sunlight for photosynthesis. Some species may have survived beneath thin ice where enough light could still pass through. Others may have lived in isolated pools of open water or near volcanic regions where melting occurred. Once warmer conditions returned, these surviving populations could spread again across the oceans. Scientists continue studying tiny fossils from rocks formed before, during, and after the snowball Earth events. These fossils help reveal which organisms survived and how life changed across these long periods. Although many species may have disappeared, enough survived for Earth's living systems to recover after the climate became warmer. Some researchers believe that these severe environmental pressures may have influenced later biological developments. Surviving organisms had to adapt to changing conditions over millions of years. After the ice ages ended, warmer oceans and changing chemistry may have created opportunities for new forms of multicellular life to spread into many different environments. The chemistry of the oceans changed greatly during these freezing periods. Ice covering much of the ocean surface reduced mixing between the atmosphere and seawater. Oxygen levels in some deep waters may have fallen because fresh oxygen from the atmosphere could not easily dissolve into the oceans beneath thick ice. Different chemical reactions became more important under these conditions. Iron dissolved in deep ocean water may have accumulated while oxygen remained scarce. After the glaciers melted and oxygen once again mixed more freely into seawater, iron reacted with oxygen and formed minerals that settled onto the ocean floor. Some rock formations created during this time preserve evidence of these chemical changes. Scientists examine tiny amounts of different chemical forms of carbon, sulfur, oxygen, and other elements preserved inside ancient rocks. These chemical records provide information about temperatures, ocean conditions, volcanic activity, and the movement of materials through Earth's atmosphere and oceans. Modern laboratory equipment allows researchers to measure extremely small differences in these elements, helping them reconstruct events that happened hundreds of millions of years ago. The movement of continents also influenced ocean circulation. As continents shifted into different positions, they changed the pathways through which ocean currents flowed. These currents transport heat around the planet. Different continental arrangements could therefore affect how easily warm water reached higher latitudes, or how cold water spread toward the equator. Such changes likely work together with atmospheric changes to shape global climate. Earth's orbit around the Sun also changes slowly over long periods. Small variations in the shape of the orbit, the angle of Earth's axis, and the direction in which the axis points affect how sunlight is distributed across the planet. These orbital changes influence the growth and melting of ice sheets. During the snowball Earth events, however, scientists believed these orbital effects alone were not strong enough to explain the extreme freezing. Instead, they likely worked alongside larger changes involving greenhouse gases and continental positions. Volcanic eruptions continued throughout the frozen ages because Earth's interior remained hot. Magma still rose from deep underground. New ocean crust continued forming along underwater mountain ranges. Volcanoes released carbon dioxide, water vapor, sulfur gases, and many other materials into the atmosphere. Since weathering was greatly reduced beneath widespread ice, carbon dioxide gradually accumulated instead of being removed. This slow build-up became one of the main explanations for how the planet eventually escaped from its frozen state. Researchers used powerful computer climate models to test different ideas about the snowball Earth events. These models include information about sunlight, atmospheric gases, ocean circulation, cloud formation, ice growth, and many other processes. By changing different conditions inside these models, scientists can examine whether widespread freezing becomes possible and how melting might begin. New discoveries continue improving these models, although uncertainties remain. Not every scientist agrees that Earth became completely frozen. Some support an alternative idea known as slushball Earth. According to this view, large parts of the planet were covered with ice, but belts of open ocean remained near the equator. These open waters would have provided larger areas where sunlight reached the sea, making survival easier for photosynthetic organisms. Supporters of this idea argue that some geological evidence can also fit this explanation. The discussion continues because the ancient evidence is incomplete and sometimes difficult to interpret. The search for answers involves researchers from many scientific fields. Geologists study rocks and sediments. Paleontologists examine fossils. Chemists investigate ancient chemical signals. Physicists help develop climate models. Biologists study how living organisms survive under extreme cold today. Information from all of these fields helps build a clearer picture of Earth's distant past. Modern icy environments provide useful information for understanding ancient freezing events. Antarctica contains thick ice sheets, hidden lakes, dry valleys, glaciers, and permanently frozen ground. Greenland also preserves large ice sheets that scientists study carefully. Although these places are not exact copies of snowball Earth conditions, they help researchers understand how ice moves, how organisms survive in cold environments, and how frozen landscapes change over time. Microorganisms discovered inside Antarctic ice, beneath glaciers, and within frozen lakes show that life can survive under conditions once thought impossible. Some remain active at very low temperatures. Others grow extremely slowly, using very small amounts of energy. These discoveries support the idea that simple life could have survived Earth's ancient global freezing events even if conditions became extremely harsh. Weather during the age of early life was never steady for long periods. The planet was still changing in many ways, and the atmosphere, oceans, and land continued to develop over very long stretches of time. During this part of Earth's history, weather played an important part in shaping the conditions that allowed life to spread and slowly become more varied. The earliest living organisms did not appear in a world with blue skies, fresh air, forests, animals, or flowering plants. Instead, they lived on a planet where the air had very little oxygen, volcanic activity remained common, the sun gave off less heat than it does today, and many parts of the surface experienced changing conditions that affected where life could survive. During the earliest stages of life, the atmosphere contained gases released mainly by volcanoes. These gases included water vapor, carbon dioxide, methane, nitrogen, sulfur compounds, and smaller amounts of other gases. Oxygen was almost completely absent. The lack of oxygen meant that the atmosphere worked very differently from today's atmosphere. Many of the living things that exist today could not have survived under these conditions. The earliest organisms did not need oxygen because they had developed ways to live without it. These simple forms of life found places where they could grow and reproduce in water, especially where conditions remained stable enough for survival. Weather during this time was closely connected to the condition of the atmosphere. Water continued moving through the early water cycle. Clouds formed as water evaporated from the oceans. Rain fell back to the surface, filling rivers, lakes, and seas. Winds carried moisture from one region to another. Storms developed when warm and cool air met under suitable conditions. Although the basic parts of weather already existed, the atmosphere itself was very different, which meant weather patterns also differed from those of the modern world. The oceans covered much of Earth's surface during this period. Since water stores heat for long periods, the oceans helped reduce sudden temperature changes in many regions. Even so, temperatures could still change because the atmosphere contained different gases than today. Carbon dioxide and methane trapped heat in the atmosphere. These gases helped keep the planet warm enough for liquid water, even though the young sun produced less energy than it does today. Without these greenhouse gases, much of the planet may have remained frozen for much longer periods. Rain continued to shape the surface of the planet. Falling rain slowly wore down exposed rocks. Rivers carried broken pieces of rock towards the oceans. These materials settled on the sea floor, forming thick layers of sediment over countless generations. Weathering also released important minerals into rivers and seas. Many simple organisms depended on these dissolved minerals for growth and survival. The steady movement of water therefore connected weather directly to the spread of early life. Volcanoes remained active across many parts of the world. Their eruptions released ash, gases, and molten rock onto the surface. Large volcanic eruptions sometimes changed the atmosphere by adding huge amounts of gases that affected temperatures. Ash carried into the atmosphere could block part of the sunlight for short periods, causing cooler conditions in some places. At other times, gases released from volcanoes increased the warming effect of the atmosphere over much longer periods. These changes influenced rainfall, ocean temperatures, and the places where living organisms could survive. The earliest life forms were very small, most consisted of only one cell. These tiny organisms lived mainly in water because water protected them from harmful sunlight that reached Earth's surface. At that time, there was no thick ozone layer high in the atmosphere. Without this protective layer, strong ultraviolet radiation from the sun reached the surface more easily. Water acted as a natural shield, allowing many simple organisms to survive beneath its surface. Weather affected shallow coastal waters in many ways. Tides moved water back and forth across coastal areas. Rain changed the amount of fresh water entering the oceans through rivers. Storms stirred ocean water, mixing nutrients from different depths. Winds pushed surface water across great distances. These processes carried nutrients and small living organisms from one place to another. As a result, weather became one of the many natural forces that helped spread life across larger areas. Many of the earliest organisms obtained energy directly from chemicals found in their surroundings. Others later developed the ability to use sunlight to make food. This process, known as photosynthesis, marked one of the greatest changes in Earth's history. Early photosynthetic organisms captured sunlight and used it to produce food while releasing oxygen as a waste product. At first, this oxygen did not remain in the atmosphere because it reacted with many substances already present in the oceans and rocks. Iron dissolved in seawater reacted with the newly produced oxygen. This reaction caused iron to form solid minerals that settled onto the ocean floor. Over very long periods, thick layers of iron-rich rocks formed in many parts of the world. These rocks provide important evidence showing that oxygen production had begun, even though very little oxygen had yet entered the atmosphere. Weather continued influencing these changes through rainfall, river flow, and ocean circulation. Rivers carried dissolved minerals into the oceans, where they mixed with oxygen released by early photosynthetic organisms. Ocean currents spread oxygen and nutrients across different regions. Wind helped move surface waters, increasing mixing in some areas. These natural processes allowed oxygen-producing organisms to spread into new environments. As more photosynthetic organisms appeared, oxygen production slowly increased. This change happened over an extremely long period. The atmosphere did not suddenly become rich in oxygen. Instead, oxygen first reacted with many materials already present on Earth. Only after these materials became less available did oxygen begin building up in the atmosphere itself. The increase in oxygen changed weather in important ways. Oxygen allowed the gradual formation of ozone high above Earth's surface. Ozone absorbed much of the harmful ultraviolet radiation coming from the sun. As this protective layer slowly developed, conditions near the surface became safer for many forms of life. Although life still remained mostly in water for a very long time, the improved protection opened new possibilities for future development. The rise of oxygen also changed the chemistry of the atmosphere. Different gases affected temperatures in different ways. Methane, which had been an important greenhouse gas, became less abundant because oxygen reacted with it. This reduced part of the warming effect that methane had provided. As methane levels dropped, global temperatures also changed. Scientists believe this contributed to major cooling events that affected weather across much of the planet. Cooling temperatures allowed glaciers to expand during certain periods. Ice covered large regions of the surface. Weather became colder over wide areas. Snow remained on the ground for longer periods. Ice reflected sunlight back into space, helping maintain cooler temperatures. These changes affected ocean circulation, rainfall patterns, and the habitats where many organisms lived. Even during colder periods, life continued surviving. Many organisms remained in oceans beneath ice-covered regions or near areas where liquid water stayed available. Some survived close to volcanic activity on the seafloor, where heat from Earth's interior created suitable conditions. Others lived in shallow waters that received enough sunlight for photosynthesis whenever ice became thin or broke apart. Weather during these colder periods remained active. Snow fell over large regions. Strong winds moved across icy landscapes. Seasonal changes continued wherever they existed. Ocean currents still transported heat between different regions, although changing temperatures sometimes altered their paths. Rain continued falling in places where temperatures remained above freezing. As the climate warmed again after cold periods, melting ice returned large amounts of fresh water to the oceans. Sea levels rose as glaciers melted. Coastal environments changed. Rivers carried fresh sediments into the seas. New habitats became available for many simple organisms. These environmental changes allowed life to spread into regions that had previously been covered by ice. Throughout this age, continents slowly moved because of plate tectonics. Land masses changed position over millions of years. These movements influenced weather by changing ocean currents, wind patterns, and rainfall. Mountains formed as plates collided. Mountains affected the movement of air, creating wetter conditions on one side and drier conditions on another. Even though the continents looked very different from today's world, the interaction between land, oceans, and atmosphere already shaped weather patterns. Rainfall remained one of the most important parts of Earth's weather system. Continuous rainfall supplied rivers that carried minerals towards the oceans. Rivers also transported nutrients that supported growing populations of microorganisms. Floods occasionally changed coastlines and shallow marine environments. Sediments buried older layers while creating new places where life could continue growing. The oceans themselves experienced changing temperatures. Surface waters warmed under sunlight, while deeper waters often remained cooler. Wind mixed these layers to different degrees, depending on local conditions. Ocean circulation transported heat from warmer regions toward cooler regions. These movements also carried oxygen and nutrients across large distances. Many organisms depended on these circulating waters for survival. Simple life gradually became more widespread because changing weather created many different environments. Some organisms adapted to warmer shallow seas. Others survived in deeper water with lower temperatures. Certain microorganisms lived near volcanic vents, where heated water carried dissolved minerals from Earth's interior. Different weather conditions across the planet created opportunities for life to occupy many habitats. The growing presence of oxygen slowly allowed organisms to develop new ways of obtaining energy. Using oxygen released much more energy from food than earlier methods. This greater energy supply supported the gradual evolution of larger and more complex cells. These more advanced cells eventually formed the foundation for the wide variety of plants, animals and fungi that appeared much later in Earth's history. Weather continued affecting every stage of this biological development. Changes in rainfall influenced river systems. River systems carried nutrients into coastal waters. Ocean temperatures affected the speed of chemical reactions inside marine environments. Winds helped circulate surface waters. Storms mixed nutrients from deeper regions into sunlit waters, where photosynthetic organisms could use them. Seasonal changes influenced the amount of sunlight reaching different parts of the planet, affecting the growth of organisms that depended on photosynthesis. The age of early life covered an immense span of time, allowing slow environmental changes to build upon one another. Weather did not remain constant throughout these ages. warm periods alternated with colder intervals. Wet regions shifted as continents moved. Ocean circulation changed as coastlines changed shape. Volcanic eruptions repeatedly altered atmospheric conditions. Each of these changes influenced where life could survive, spread, and slowly develop into increasingly complex forms. The climate during the age of dinosaurs changed many times across the very long period when dinosaurs lived on Earth. This age lasted for well over 160 million years. During that time, the land, oceans, atmosphere, and living things all changed again and again. The weather was not always the same from one place to another or from one period to another. Some regions stayed warm throughout the year, while others had clear wet and dry seasons. Some places received heavy rainfall, while others remained dry for long periods. There were forests, rivers, lakes, swamps, deserts, coastlines, mountains, and open plains. Every kind of environment influenced the animals and plants that lived there. The world of the dinosaurs began after a time of great change. Earlier periods had ended with a major extinction that removed many kinds of living things. As life slowly recovered, new groups of animals spread across the land. Dinosaurs became one of the most successful groups. They lived in environments that were shaped by changing weather, moving continents, volcanic activity, and changing sea levels. The climate played an important part in where different kinds of dinosaurs could live and how they survived. At the beginning of the dinosaur age, most of Earth's land was joined together in one huge landmass called Pangaea. Because so much land was connected, the middle parts of this giant continent were very far from the oceans. The sea could not easily bring moisture into these inland areas. As a result, many places in the center of the continent were dry. Rain did not fall regularly in every region. Some places received rain only during certain parts of the year. Rivers often became smaller during dry times and then filled again after seasonal rains returned. The coastlines were usually wetter because they were closer to the oceans. Moist air moved inland from the sea and brought rainfall. Thick forests grew in many coastal regions where water was available throughout much of the year. Plants grew well in these places because they received enough sunlight, warmth, and moisture. These forests became home to many kinds of dinosaurs, insects, reptiles, amphibians, and early mammals. Temperatures during much of the dinosaur age were generally warmer than those of today. There were long periods when large ice sheets were absent from the poles. Because there was little permanent ice, sea levels often stayed higher than they do today. Warm oceans also affected the atmosphere. They released large amounts of water vapor, which helped clouds form and brought rain to many regions. The atmosphere during much of the dinosaur age was different from the atmosphere of today. Levels of carbon dioxide were often much higher than modern levels. Volcanoes released large amounts of gases into the air over very long periods. Carbon dioxide trapped heat in the atmosphere, helping keep the planet warm. This warming influenced temperatures across both land and sea. Volcanic activity remained an important part of the dinosaur world. Many volcanoes erupted across different regions over millions of years. Each eruption released ash, gases, and molten rock. Ash sometimes covered nearby forests and rivers. Gases entered the atmosphere and influenced the climate. Some eruptions caused short periods of cooling because volcanic ash blocked part of the sunlight. Later, carbon dioxide released from volcanoes helped increase temperatures again. These natural events became part of the changing climate that affected plants and animals. Rainfall was not evenly spread across the world. Some places received heavy rain almost every year. Rivers remained full, lakes stayed large, and wetlands supported rich plant life. Ferns, horsetails, cycads, conifers, and many other plants covered the land. Plant-eating dinosaurs found plenty of food in these regions. Large groups of animals could live together because enough vegetation grew to support them. Other places remained dry for much of the year. Strong sunlight heated the land during the day. Temperatures often became very high. Water sources became limited during dry seasons. Only plants that could survive with less water continued growing. Dinosaurs living in these places likely traveled between areas where food and water were available as conditions changed throughout the year. Seasonal weather became an important part of life in many regions. Wet seasons brought heavy rain that filled rivers and lakes. Plants quickly produced fresh leaves and stems. Food became more abundant for plant-eating animals. During dry seasons, many water sources became smaller. Some rivers slowed while others disappeared until rain returned. Animals needed to adjust their movements to find enough food and water. Storms were common in many parts of the dinosaur world. Warm temperatures caused water to evaporate from the oceans, lakes, and rivers. As warm, moist air rose into the atmosphere, clouds formed. These clouds often produced heavy rain, thunder, and lightning. Strong winds sometimes damaged forests by breaking branches or knocking down trees. Floods changed river channels and spread fresh soil across floodplains. Flooding shaped many dinosaur habitats. Rivers overflowed after long periods of rain. Water spread across wide areas of land. Sediment settled over the floodplains as floodwaters slowly moved away. These fresh layers of soil helped new plants grow. Floods also buried fallen trees, leaves, animal remains, and footprints beneath mud. Millions of years later, these buried materials became valuable clues for scientists studying dinosaur environments. Many fossils found today formed because animals were buried quickly by mud after floods. Rapid burial protected bones from weathering and scavengers. Over long periods, the bones slowly changed into fossils as minerals replaced the original material. The surrounding rocks preserved information about the climate, rivers, lakes, and soils that existed when those animals lived. The warm climate allowed forests to grow across large parts of the world. Conifer trees became especially common. Their seeds provided food for some animals. Their branches offered shelter for small creatures. Ferns covered the ground beneath taller trees. Mosses and other small plants grew wherever moisture remained available. Thick plant growth supported many different plant-eating dinosaurs. Large dinosaurs needed enormous amounts of food every day. Warm weather and plentiful rainfall in many regions helped plants grow quickly. This steady supply of vegetation allowed giant plant-eaters to survive. Long-necked dinosaurs reached leaves growing high above the ground. Other species fed on lower plants, shrubs, and young trees. Different feeding habits reduced competition for food within the same area. The climate also affected meat-eating dinosaurs. They depended on healthy populations of plant-eaters for food. Where plants flourished, plant-eating dinosaurs became more numerous. Areas with many prey animals also attracted large predators. Weather therefore influenced entire food chains by controlling plant growth, water supplies, and the movement of animals. Some parts of the dinosaur world experienced long dry periods followed by sudden heavy rains. These changing conditions shaped the landscape. Dry riverbeds sometimes remained empty for months before becoming powerful rivers again after seasonal storms. Such changes influenced where animals traveled and where they gathered during different times of the year. Scientists have found ancient soils that formed during the dinosaur age. These soils contain minerals that provide information about rainfall and temperature. Certain soil layers formed only under wet conditions, while others developed in dry climates. By studying these ancient soils, researchers learn about the environments where dinosaurs once lived. Tree fossils also preserve valuable climate information. Some fossil trees show growth rings. These rings formed as trees grew during favourable seasons and slowed during less favourable periods. The width and pattern of these rings helps scientists understand changes in rainfall and temperature from year to year. Although many dinosaur forests grew in warm climates, seasonal changes still influenced tree growth in several regions. Ancient lakes preserved another record of dinosaur weather. Layers of mud settled on lake bottoms year after year. Tiny particles carried by rivers entered these lakes during rainy seasons. Pollen, leaves, insects, and small animals also became trapped within the mud. Millions of years later, these layers allow scientists to study ancient rainfall, nearby plants, and seasonal weather patterns. The ocean strongly influenced climate throughout the dinosaur age. Warm ocean currents carried heat across great distances. These currents helped spread warmth to coastal regions and affected rainfall patterns. Changes in ocean circulation sometimes altered temperatures in different parts of the world. Marine life also responded to these changes as sea temperatures shifted over long periods. Sea levels rose and fell many times during the dinosaur age. When sea levels increased, shallow seas spread across low-lying land. These inland seas changed local climates by bringing moisture farther inland. Coastal regions expanded, creating new habitats for plants and animals. When sea levels later dropped, new land became exposed and rivers carved fresh paths across the landscape. As millions of years passed, Pangaea slowly began breaking apart. The continents gradually moved away from one another. New oceans formed between them. This movement changed wind patterns, rainfall, and ocean currents. Different climates developed as the continents continued moving toward their present positions. Forests expanded in some regions, while deserts developed in others. The continued movement of the continents created mountains in certain areas. Mountains influenced local weather by affecting winds and rainfall. Some mountain slopes received abundant rain, while other, nearby regions became much drier. Rivers flowing from these mountains carried fresh water and nutrients into lower lands, supporting rich plant life where many dinosaurs lived. The poles during much of the dinosaur age were warmer than they are today. Forests even grew in high northern and southern regions. Dinosaurs lived in these polar forests despite experiencing long periods of darkness during part of the year because of Earth's tilt. Even without permanent ice sheets, seasonal changes still affected temperatures and daylight in these regions. Many polar dinosaurs adapted to these changing conditions. During months of continuous daylight, plants grew rapidly. During darker months, plant growth slowed. Animals living there adjusted their feeding and behavior according to the changing seasons. Some species may have remained throughout the year, while others may have traveled to different regions depending on food availability. The climate continued changing throughout the long history of the dinosaurs. Some periods became warmer, while others experienced temporary cooling caused by volcanic activity, changing sea levels, or shifts in atmospheric gases. These gradual changes influenced where different species could survive and how ecosystems developed across the planet. Ancient supercontinents played a major part in shaping the climate of Earth over an extremely long period of time. They changed the way heat moved across the planet, influenced where rain fell, affected the size and location of deserts, guided the flow of ocean water, and even changed the direction of winds. These giant landmasses formed slowly through the movement of Earth's outer rocky shell. They also broke apart very slowly, creating new oceans and moving continents into new places. These changes happened over millions of years, but they had lasting effects on weather, climate, and life. A supercontinent is a huge landmass made up of most or nearly all of Earth's continents joined together. Earth has experienced several supercontinents during its long history. Two of the best known are Rodinia and Pangaea. Each one existed at a different time and had its own influence on climate. Scientists study ancient rocks, fossils, minerals, and many other clues to understand how these giant landmasses affected the planet. The surface of Earth is divided into large rocky plates that slowly move. These plates float on the hotter material deep inside the planet. Heat from Earth's interior causes this movement. As the plates move, continents travel across the surface. Sometimes they move toward one another and join together. At other times, they pull apart. This movement is very slow. It usually takes many millions of years for major changes to happen. Rodinia formed more than 1 billion years ago. Scientists believe that it came together during a very long period as many ancient continents slowly collided. At that time, much of Earth's land was connected into one enormous mass. Large oceans surrounded this landmass, and the arrangement of land and sea was very different from the world we know today. The position of Rodinia affected the amount of sunlight received in different regions. Some parts of the supercontinent were located closer to the equator, where sunlight was stronger throughout the year. Other parts were farther away, where temperatures were lower. Because Rodinia was so large, many places deep inside the landmass were very far from the sea. This distance had a strong effect on rainfall and temperature. Oceans provide moisture that later falls as rain or snow. Winds carry this moisture over land. As moist air travels farther inland, it gradually loses much of its water through rainfall. By the time it reaches the center of a very large continent, much less moisture remains. This often creates dry conditions. For this reason, the centers of ancient supercontinents were likely much drier than coastal regions. The edges of Rodinia probably received more rain because they were closer to the oceans. Moist winds could easily reach these areas. Rivers flowed more often and lakes may have been more common. Plants and simple living organisms that depended on water had better conditions near many coastal areas. Inland regions likely experienced long dry periods with limited rainfall. Temperature also changed greatly across Rodinia. Coastal regions usually had smaller changes between warm and cool seasons because nearby oceans stored heat and slowly released it. Inland regions lacked this effect. During warm seasons, temperatures could become very high because the land heated quickly. During cooler seasons, temperatures could fall much lower because land also lost heat quickly. The size of Rodinia affected wind patterns across the planet. Winds form because different parts of Earth receive different amounts of heat from the sun. As warm air rises and cooler air moves in to replace it, large air circulation systems develop. A giant landmass changed these air movements by creating large areas that heated and cooled differently from nearby oceans. Mountains also played an important part in the climate of Rodinia. When continents collide, they often create long mountain ranges. These mountains affected the movement of moist air. As winds carrying moisture reached mountain slopes, the air rose higher into the atmosphere. Rising air cooled, causing water vapor to form clouds and rain. Areas on one side of the mountains often received heavy rainfall, while regions on the opposite side remained much drier, because most of the moisture had already fallen. Scientists believe that Rodinia may have played a role in some of Earth's earliest widespread ice ages. During parts of its history, glaciers spread across large areas of the planet. Some scientists think that the arrangement of land near the equator may have helped remove large amounts of carbon dioxide from the atmosphere. Rainwater reacted with rocks, slowly breaking them down in a process called weathering. This process trapped carbon dioxide over very long periods. As carbon dioxide levels dropped, Earth's atmosphere held less heat, allowing temperatures to fall. Lower temperatures encouraged the growth of ice sheets. Ice reflects a large amount of sunlight back into space. As more ice formed, even less solar heat was absorbed by Earth's surface. This helped temperatures remain lower. Scientists continue to study these events because many details are still being investigated. But there is strong evidence that the position of continents influenced these climate changes. Eventually, Rodinia began to break apart. Deep beneath the surface, rising hot material weakened parts of the crust. Large cracks developed and new oceans slowly formed between separating landmasses. As the continents drifted away from one another, coastlines became much longer. More land was located near the sea, allowing moist air to travel farther inland. The breakup of Rodinia gradually changed rainfall patterns around the world. Regions that had once been dry because they were far from the sea became closer to new coastlines. Rainfall increased in many places. Rivers formed in new areas, carrying sediments toward the oceans. New environments appeared, giving living organisms many different places to survive. Ocean currents also changed after Rodinia separated. Ocean currents move warm and cool water around the planet. They help spread heat from one region to another. When continents move, they open and close pathways through which ocean water flows. A new arrangement of continents changes the direction and strength of these currents. This affects temperatures, rainfall, and weather over wide areas. As time continued, Earth's continents moved through many different positions. Smaller continents joined and separated many times before another great supercontinent formed. This later supercontinent became known as Pangaea. It formed about 335 million years ago and remained together for many millions of years before beginning to split apart. Pangaea stretched across a large part of Earth's surface. It contained nearly all of Earth's major land areas connected into one enormous continent. A vast ocean surrounded it, while another large sea extended into parts of the interior. Even so, huge regions remained very far from the nearest coastline. The climate of Pangaea was strongly shaped by its enormous size. Coastal regions often received regular rainfall from moist ocean winds. Inland areas were much drier because little moisture reached them. Many deserts developed across the interior of the supercontinent. Evidence for these ancient deserts can still be found today in layers of sandstone created by wind-blown sand. These deserts formed because moist air lost much of its water before reaching the center of the continent. The farther the air traveled over land, the less moisture remained. As a result, clouds became less common, rainfall decreased, and dry conditions lasted for long periods. The lack of moisture affected plants and animals living in these regions. Only species able to survive with limited water could live successfully in such environments. Rivers often became seasonal, flowing mainly during wetter times. Some lakes dried up as evaporation removed water faster than rainfall could replace it. Mass extinctions are some of the biggest events in the history of Earth. They happened when a very large number of plant and animal species disappeared within a relatively short period in geological time. These events changed life across the planet and opened the way for new forms of life to appear and spread. Scientists have found that climate played an important part in many of these extinctions. Rapid changes in temperature, powerful volcanic eruptions, asteroid impacts, and major changes in the oceans all affected the conditions that living things depended on for survival. Some of these changes happened over thousands of years, while others may have happened much more quickly. Even when the main cause was something like a giant asteroid impact, the climate changes that followed often became one of the biggest reasons why so many species disappeared. The climate of Earth has never remained exactly the same. Throughout the planet's long history, temperatures have risen and fallen many times. Rainfall patterns have changed, sea levels have moved up and down, glaciers have expanded and melted, and the amount of oxygen and carbon dioxide in the atmosphere has changed. Living things can often adapt when these changes happen slowly. Plants and animals can move into new places, develop new ways of surviving, or slowly change over many generations. Problems become much greater when climate changes happen too quickly. Many species cannot move fast enough or adapt quickly enough. Food becomes harder to find, breeding becomes difficult, and entire ecosystems begin to fail. Climate affects every part of life. It controls where forests grow, where deserts form, how much fresh water is available, and how warm or cold different parts of the world become. Climate also affects the oceans by changing water temperatures, ocean currents, and the amount of oxygen dissolved in seawater. Since all living things depend on stable environments, sudden climate changes can create problems across the entire planet. Many scientists recognize several major mass extinction events during Earth's history. Each event had its own causes and its own effects, but climate changes appeared again and again as an important part of the story. Sometimes volcanic eruptions filled the atmosphere with gases that changed global temperatures. Sometimes the movement of continents changed ocean circulation and weather patterns. Sometimes an asteroid struck Earth and filled the atmosphere with dust that blocked sunlight. These different events often led to major climate changes that lasted for many years or much longer. The oldest of the major mass extinctions happened during the Ordovician period, around 444 million years ago. At that time, most life lived in the oceans. Sea creatures such as brachiopods, trilobites, corals, and many other marine animals filled shallow seas. During this period, Earth experienced major climate changes that caused temperatures to fall. Large ice sheets formed across parts of the southern landmass. As more water became trapped in glaciers, sea levels dropped. Many shallow seas disappeared as the water moved into growing ice sheets. These shallow seas were home to countless marine species. When the water became shallower or disappeared completely, many animals lost their habitats. At the same time, colder ocean temperatures created even more stress for marine life. Some species could survive colder conditions, but many could not. The changing climate continued to affect ocean circulation, nutrient movement, and the distribution of oxygen in seawater. As these changes spread, many species became extinct. After this cold period, the climate began to warm again. Ice sheets melted and sea levels rose once more. While this warming restored some habitats, it also brought new problems. Rapid environmental changes forced surviving species to face another round of difficult conditions. Scientists believe that both the cooling period and the later warming helped drive this extinction event. Another major extinction happened near the end of the Devonian period, around 372 million years ago, with additional losses continuing until about 359 million years ago. During this time, life had become more diverse. Large coral reefs covered many shallow seas, and early forests spread across land. Fish had become very successful in the oceans and rivers. Some animals had also begun exploring life on land. The causes of this extinction appear to have involved several different climate-related changes. One important factor was the spread of large forests. As forests expanded, They removed large amounts of carbon dioxide from the atmosphere through photosynthesis. Lower carbon dioxide levels may have contributed to global cooling. Cooler temperatures affected rainfall, ocean circulation, and sea levels. The oceans also experienced serious changes. Many parts of the oceans lost much of their oxygen. Scientists call this ocean anoxia. Oxygen is necessary for most marine animals. Without enough oxygen, fish, shellfish, and many other creatures cannot survive. Large areas of low oxygen water spread across the seas, killing many marine species. Volcanic activity may also have played a role by releasing gases into the atmosphere and changing climate conditions. Changes in nutrient flow from rivers into the oceans may have encouraged large growths of algae. When these algae died and decayed, they used up even more oxygen in the water. This created even larger low-oxygen zones that became deadly for marine life. The largest mass extinction in Earth's history happened near the end of the Permian period, around 252 million years ago. This event is sometimes called the Great Dying because it eliminated most species living at that time. It affected both marine life and life on land. Scientists estimate that the great majority of marine species disappeared, along with many land animals and plants. One of the main causes of this disaster appears to have been enormous volcanic eruptions in what is now Siberia. These eruptions continued for a very long time and covered huge areas with lava. They released massive amounts of carbon dioxide, methane, sulfur gases, and other materials into the atmosphere. Carbon dioxide trapped more heat in the atmosphere, causing global temperatures to rise. Higher temperatures changed weather patterns, increased evaporation, and placed stress on plants and animals. Many regions became hotter than many species could tolerate. Forests declined, rivers changed, and ecosystems became unstable. Sulfur gases released by volcanoes also formed tiny particles in the atmosphere that reflected sunlight. These particles may have caused temporary cooling before the warming caused by greenhouse gases became stronger. This meant that living things experienced changing climate conditions over time instead of one steady environment. The oceans suffered greatly during this period. Warmer water holds less oxygen than cooler water. As ocean temperatures increased, oxygen levels fell. Ocean circulation also weakened in some areas, making it harder for oxygen-rich water to reach deeper parts of the oceans. Large regions became almost completely without oxygen. Bacteria that thrive without oxygen increased in these conditions. Some of these bacteria produced hydrogen sulfide gas. This poisonous gas may have entered shallow waters and even reached the atmosphere in some places. Hydrogen sulfide is dangerous for many forms of life. It damaged marine ecosystems and may also have harmed plants and animals living on land. The warming climate also changed ocean chemistry. Increasing carbon dioxide dissolved into seawater and formed carbonic acid. This process made the oceans more acidic. Many marine animals build shells or skeletons from calcium carbonate. More acidic water made it harder for these animals to grow and survive. Food chains began to break apart. Tiny organisms that formed the base of many marine food webs declined in some areas. Larger animals that depended on them also suffered. Predators lost their prey. Plant-eating animals found less food. Carnivores found fewer animals to hunt. The collapse spread through ecosystems across the world. Life on land also faced serious difficulties. High temperatures increased water loss from soils and plants. Some regions became much drier. Wildfires may have become more common as forests dried. Plants disappeared from many areas, leaving herbivores without enough food. Carnivores also declined as their prey became scarce. Many insect groups were affected as well. Insects usually survive environmental changes very successfully. Yet this extinction harmed many insect species. Their losses show how severe the environmental conditions became during this period. Recovery from this extinction took a very long time. Ecosystems remained damaged for millions of years. New species slowly evolved to replace those that had disappeared. Different groups of reptiles, marine animals, plants, and other organisms gradually spread into habitats left empty after the extinction. Another major extinction happened near the end of the Triassic period, around 201 million years ago. At this time, the supercontinent Pangaea was beginning to break apart. Large cracks opened in Earth's crust, allowing huge volcanic eruptions to occur across wide regions. These eruptions released great amounts of carbon dioxide into the atmosphere. Global temperatures increased, rainfall patterns changed, and many habitats became less stable. Some areas experienced more drought, while others received heavier rainfall. Seasonal weather became more extreme in many places. The oceans again experienced warming and falling oxygen levels. Marine ecosystems became increasingly difficult places for many species to survive. Coral reefs declined, shellfish disappeared from some regions, and many marine reptiles faced new environmental pressures. Plants also experienced changing conditions. Some forests declined while different kinds of vegetation spread into newly suitable environments. Animals that depended on older plant communities often struggled to find enough food. Many reptile groups became extinct during this event. Their disappearance allowed dinosaurs to become the dominant large land animals during the Jurassic period. This change happened because empty habitats became available after many older species disappeared. The most famous mass extinction happened near the end of the Cretaceous period. Around 66 million years ago, this extinction ended the age of non-avian dinosaurs. Scientists have gathered strong evidence showing that a large asteroid struck Earth near what is now the Yucatan Peninsula in Mexico. The impact released an enormous amount of energy. Rock was melted and thrown high into the atmosphere. Dust, ash, and tiny particles spread around the world. These materials blocked much of the sunlight reaching Earth's surface. Without enough sunlight, temperatures dropped quickly. Photosynthesis slowed because plants needed sunlight to produce food. Many plants died or stopped growing. Animals that depended directly on plants soon faced food shortages. Carnivores also suffered because their prey became scarce. The darkness may have lasted for many months. Cooler temperatures spread across much of the planet. Growing seasons became shorter or disappeared in many places. Forests experienced heavy damage. Many freshwater ecosystems also changed as plant growth declined. The asteroid impact probably triggered huge wildfires across large areas. Burning forests released smoke and additional particles into the atmosphere. These materials added to the dust already blocking sunlight. Large earthquakes followed the impact. Massive sea waves spread across nearby coastlines. These events destroyed many local ecosystems immediately, while the climate changes that followed affected the entire planet. Scientists also know that large volcanic eruptions were taking place in what is now India around the same general time. These eruptions formed the Deccan Traps. They released carbon dioxide and sulfur gases into the atmosphere over long periods. Some researchers believe these eruptions had already begun changing climate conditions before the asteroid struck. The impact and volcanic activity together may have created even greater environmental stress. The oceans also changed after the impact. Less sunlight meant that tiny ocean plants, called phytoplankton, declined sharply. These organisms formed the base of many marine food chains. As they disappeared, many sea creatures lost their main food source. Marine reptiles, ammonites, and many plankton species became extinct. Not every species disappeared. Birds survived because they belonged to one branch of dinosaurs that managed to continue through the extinction. Small mammals also survived in greater numbers than many larger animals. Their small size, varied diets, and ability to shelter underground may have helped some species remain alive during the difficult conditions. Climate changes continued after the immediate effects of the asteroid impact. Once the dust settled, carbon dioxide from volcanic eruptions and fires may have contributed to later warming. Surviving species had to adapt first to cooling and darkness, and then to changing temperatures afterward. Mass extinctions did not always result from one single cause. In many cases, several different events happened close together. Volcanoes changed the atmosphere, oceans lost oxygen, continents moved into new positions, sea levels changed, asteroids struck, climate shifted. These events often worked together to create conditions that became too difficult. For many species, volcanic eruptions influence climate in several important ways. During an eruption, volcanoes release ash, sulfur gases, carbon dioxide, water vapor, and many other materials. Ash and sulfur particles can block some sunlight and cool the planet for a period of time. Carbon dioxide remains in the atmosphere much longer and contributes to warming. When volcanic eruptions continue for thousands or hundreds of thousands of years, large amounts of greenhouse gases can produce major climate changes. Large volcanic provinces have appeared several times during Earth's history. These regions formed when huge amounts of lava covered enormous areas. Such eruptions released gases over very long periods. The atmosphere gradually changed, temperatures increased, rainfall patterns shifted, and ocean chemistry changed. These long-lasting environmental changes often placed heavy pressure on ecosystems. Asteroid impacts affect climate differently. Instead of changing the atmosphere slowly, they create sudden changes. Dust and smoke fill the sky almost immediately. Sunlight decreases rapidly, temperatures fall, plants lose the light needed for photosynthesis. Food chains begin breaking apart within a short time. If fires spread widely, additional smoke makes the darkness even greater. Changing oceans have also played an important part in many extinction events. Ocean currents move warm and cold water around the world. They also carry oxygen and nutrients. If ocean circulation changes, entire marine ecosystems can be affected. Warmer water usually contains less dissolved oxygen. Many sea animals need oxygen-rich water to survive. Falling oxygen levels can kill fish, shellfish, and countless smaller organisms. Ocean acidification creates another serious problem. Carbon dioxide enters seawater from the atmosphere. This changes ocean chemistry and lowers the water's pH. Shell-building organisms have greater difficulty forming strong shells and skeletons. Since many food chains begin with these organisms, the effects spread throughout marine ecosystems. Sea level changes also affect climate and extinction. When sea levels fall, shallow seas disappear. These shallow waters often contain rich ecosystems filled with marine life. Their disappearance removes habitats that countless species depend upon. Rising sea levels create different challenges by flooding coastal environments and changing ocean circulation. Continental movement has influenced climate throughout Earth's history. As continents slowly drift across Earth's surface, they change the arrangement of oceans and land. Ocean currents take different paths. Mountains rise through tectonic activity and change rainfall patterns. polar regions may receive large landmasses that allow glaciers to grow. Tropical regions shift as continents move closer to or farther from the equator. These changes affect temperatures and rainfall over millions of years. Plants play an important role in climate because they remove carbon dioxide from the atmosphere. Large changes in plant life can influence atmospheric conditions over long periods. Forest expansion may reduce carbon dioxide levels, while widespread forest loss allows more carbon dioxide to remain in the atmosphere. During some extinction events, damaged forests reduced Earth's ability to remove greenhouse gases. Methane has also influenced climate during some extinction events. Methane traps much more heat than carbon dioxide over shorter periods. Large releases of methane may have happened from frozen deposits beneath the oceans or from changing wetlands. These releases could have increased global warming and added further stress to ecosystems already facing difficult conditions. Life often becomes more vulnerable when environmental changes happen together. A species already struggling with rising temperatures may also face drought, food shortages, disease, changing rainfall, habitat loss, and increased competition. One problem alone may not cause extinction, but several problems acting together can become overwhelming. Marine ecosystems have experienced repeated losses during mass extinctions because oceans respond strongly to climate changes. Even small changes in temperature can alter breeding seasons, migration patterns, food availability, and oxygen levels. Coral reefs are especially sensitive because reef-building organisms require stable conditions. When temperatures become too warm or ocean chemistry changes, reefs decline and many animals lose their homes. Land ecosystems also experience chain reactions during climate shifts. Plants respond to changing temperatures and rainfall. Herbivores depend on those plants. Carnivores depend on herbivores. Insects pollinate flowers and serve as food for many birds and reptiles. If one important group declines, many other groups are affected. Scientists study rocks, fossils, volcanic layers, chemical elements, and ancient sediments to understand these extinction events. Fossils show which species disappeared and which survived. Rock layers preserve evidence of volcanic eruptions, changing sea levels, and asteroid impacts. Tiny fossils found in ocean sediments reveal changes in ancient marine ecosystems. Chemical signatures trapped inside rocks help scientists estimate past temperatures, oxygen levels, and carbon dioxide concentrations. Ice cores cannot reach back to the oldest mass extinctions because ice does not survive for such enormous lengths of time. Instead, researchers depend on other natural records. Limestone, shale, volcanic rocks, fossil shells, and mineral deposits preserve important information about ancient climates. Scientists combine evidence from many different places around the world to build a clearer picture of what happened. About 66 million years ago, life on Earth entered a very different period. The disappearance of the non-avian dinosaurs changed the natural world in many ways. Forests, rivers, plains, mountains, wetlands, and coastlines still existed, but many of the largest animals that had ruled the land for a very long time were gone. This change opened many opportunities for mammals. They had already lived alongside dinosaurs for millions of years, but they were usually small and often stayed hidden. As the climate continued to change over time, mammals slowly spread into many different environments. Changes in temperature, rainfall, forests, grasslands, and the movement of continents helped shape the long history of mammals. Their bodies, diets, behaviors, and ways of living changed, as the planet itself continued to change. Before the disappearance of the non-avian dinosaurs, mammals were already present on Earth. Their ancestors first appeared more than 200 million years ago, during the age when dinosaurs were becoming common. Early mammals were generally small. Many were no larger than modern mice, rats, or small squirrels. Their small size helped them survive in a world where large reptiles dominated many habitats. They often searched for insects, seeds, fruits, and other small sources of food. Many were active during the night, which reduced the chance of meeting large predators during the day. They lived in burrows, trees, thick vegetation, and other protected places. These early mammals already possessed many features that later helped their descendants succeed. They had warm bodies that allowed them to stay active in different temperatures. They produced milk to feed their young. Their bodies were covered with hair or fur, which helped keep them warm. Their teeth were specialized for different jobs, making it easier to eat many kinds of food. Their brains became larger over time, allowing more complex behavior. Even though they were usually small, these features gave mammals many advantages, as environments slowly changed. The event that marked the end of the age of non-avian dinosaurs caused major changes around the world. A large asteroid struck Earth, sending huge amounts of dust, rock, and gases into the atmosphere. Wildfires spread across many regions. Sunlight reaching the ground became much weaker for a long period because dust blocked much of it. Plants struggled to grow under these conditions. Many food chains broke apart as plants disappeared and animals lost their food sources. Temperatures dropped for a time before later becoming warmer again as conditions slowly recovered. Many large animals could not survive these sudden changes. The disappearance of the non-avian dinosaurs left many habitats without their previous dominant animals. Mammals that survived this difficult period found new opportunities. They began moving into places where they had once faced heavy competition. They explored forests, open land, rivers, lakes, and coastlines. Over millions of years, they slowly became larger, more diverse, and more specialized. The world immediately after the extinction event looked different from the world before it. Forests slowly returned as plants recovered. New plant communities spread across many regions. Flowering plants became even more common. Trees produced fruits, seeds, leaves, and flowers that supported growing populations of insects, birds, and mammals. Every change in plant life created new food sources. Mammals responded by developing different diets and different ways of living. Some mammals continued eating insects because insects remained plentiful in many environments. Others began feeding mainly on fruits. Some specialized in leaves, while others ate seeds, roots, nuts, or mushrooms. Meat also became an important food source for certain mammals. Small hunters searched for insects, reptiles, birds, fish, and other mammals. Every new food source encouraged new body shapes and behaviors. Climate continued changing throughout this long period. Temperatures rose during some times and fell during others. Rainfall patterns also shifted. Some regions became wetter, while others became drier. Forests expanded during warm and wet periods. During cooler or drier times, forests sometimes became smaller, allowing more open land to appear. Mammals adapted again and again as these environmental changes continued. The early part of the age of mammals was generally warmer than today. Large forests covered many areas that are now much cooler. Even regions close to the poles supported forests. There were no large permanent ice sheets covering Antarctica or Greenland during much of this early period. Warm temperatures allowed many plants to grow over large areas, creating rich habitats for mammals. Warm forests offered many different places for animals to live. Some mammals remained on the forest floor, others climbed trees in search of food and safety. Tree branches became home to mammals that could grip bark, jump between branches, or climb with sharp claws. Living in trees encouraged changes in hands, feet, eyes, balance, and movement. These changes later became important in the evolution of several mammal groups, including the earliest primates. The first primates appeared during this warm world. They lived mainly in forests where fruits, flowers, insects, and leaves were available. Their hands and feet became better suited for grasping branches. Their eyes gradually faced more forward, giving improved depth perception. Larger brains supported more complex behavior. Warm forest environments helped these early primates spread across different regions. Many other mammal groups also expanded. Early relatives of horses, rhinoceroses, elephants, whales, bats, rodents, and carnivores appeared during these millions of years. Although these animals looked different from their modern descendants, they represented the beginnings of groups that would later spread across much of the world. Early horses were much smaller than modern horses. Many lived in forests where they fed on soft leaves and other plant material. Their feet had several toes instead of a single hoof. Forest soils allowed these smaller feet to move easily through soft ground. As climates changed much later and grasslands spread, horses gradually developed longer legs and stronger hooves suited for running across open land. The ancestors of elephants also began as much smaller animals. Some lived near rivers and wetlands where water and plants were abundant. Over millions of years, they developed larger bodies, longer trunks, and specialized teeth. Climate changes influenced where they could live and what plants they depended upon. The earliest whales began as land mammals. Their ancestors lived near rivers and coastlines. Some searched for food in shallow water while still spending much time on land. Over millions of years, they became better swimmers. Their legs gradually changed into flippers. Their tails became stronger for swimming. Their nostrils slowly moved higher on the head, eventually becoming blowholes. Oceans provided rich food supplies, and changing coastlines created many new habitats. Bats also appeared during the early age of mammals. Their wings developed from modified forelimbs with long fingers supporting thin skin. Warm climates supported many flying insects, giving bats a reliable food source. Flying allowed them to travel efficiently between feeding areas and avoid many ground predators. Rodents became one of the most successful mammal groups. Their front teeth continued growing throughout life, allowing them to chew seeds, nuts, bark, roots, and many other foods. Small body size allowed rodents to live in forests, grasslands, deserts, mountains, and wetlands. Their ability to reproduce quickly helped them survive changing conditions. Carnivorous mammals also became more diverse. Some hunted alone while others probably hunted in groups. Sharp teeth, strong jaws, keen hearing, and a powerful sense of smell helped them locate prey. As herbivorous mammals spread into different habitats, meat-eating mammals followed them into many environments. During the Paleocene and Eocene, global temperatures remained high for long periods. Forests covered much of the land. Heavy rainfall supported dense vegetation in many places. Rivers carried nutrients across wide plains. Wetlands provided homes for countless animals. Warm oceans supported rich marine ecosystems that included fish, sharks, marine reptiles that had survived earlier extinctions, turtles, and growing numbers of marine mammals. One important warming event occurred about 56 million years ago. During this period, global temperatures increased rapidly over a relatively short geological time. Large amounts of carbon entered the atmosphere. The exact sources remain an area of scientific study, but volcanic activity, methane release, and other natural processes may all have contributed. Higher temperatures affected rainfall, ocean chemistry, and plant communities. Many mammals responded by moving into new areas where conditions became suitable. Some species became smaller during this warming period, possibly because smaller bodies released heat more easily. Others shifted their diets as different plants became available. Migration became an important way for mammals to survive changing climates. Moving into new regions allowed populations to find food, water, and suitable temperatures. The movement of continents also influenced climate throughout the age of mammals. Continents slowly drifted into new positions. Oceans opened and closed between land masses. Mountain ranges rose as tectonic plates collided. Every one of these geological changes influenced wind patterns, rainfall, ocean currents, and seasonal temperatures. As mountains grew taller, they changed weather patterns. Moist air rose along mountain slopes, producing rain on one side while leaving the opposite side much drier. Forests often grew where rainfall remained abundant. Dry regions sometimes developed beyond mountain ranges. Mammals living in these different environments gradually developed different adaptations suited to local conditions. The separation of continents also affected animal populations. Groups of mammals living on isolated landmasses followed different evolutionary paths. Without regular contact, populations slowly became different species. Australia became home to many marsupials. South America also supported unique mammal communities for long periods before later connections with North America allowed animals to move between the continents. Marsupials raised their young differently from placental mammals. Very young babies continue developing inside a pouch after birth. Australia became an important centre for marsupial evolution because of its long isolation. Kangaroos, koalas, wombats, and many other marsupials eventually appeared there. Their ancestors adapted to forests, grasslands, and dry regions as Australian climates changed through time. Placental mammals spread widely across other continents. Their young developed longer inside the mother's body before birth. This reproductive strategy supported many different lifestyles, allowing placental mammals to occupy forests, deserts, mountains, grasslands, wetlands, and polar environments. Monotremes remained another unique mammal group. They lay eggs instead of giving birth to live young. Today, only a few species survive, including the platypus and echidnas. Their ancestors represent one of the earliest branches of mammal evolution. Around 34 million years ago, Earth's climate entered a cooler phase. Antarctica gradually became isolated. As ocean currents changed, powerful currents began circulating around the continent. These currents reduced the movement of warm water toward Antarctica. Large ice sheets started forming across the continent. This marked the beginning of a colder world than had existed for many millions of years. Cooling temperatures affected mammals everywhere. Forests became smaller in many regions. Grasslands expanded across broad areas. Different plants replaced some of the older forests. Animals living in shrinking forests either adapted to the new conditions, moved into remaining forests, or disappeared from certain regions. Grasslands became one of the most important environments for mammal evolution. Grasses spread widely because they could survive grazing, seasonal dryness, and periodic fires. Their roots reached deep into the soil, helping them recover after damage. Large areas of open land became covered with grasses instead of forests. Herbivorous mammals adapted to these expanding grasslands. Grazing required different teeth because grass contains tiny particles of silica that wear down tooth surfaces. Mammals that fed mainly on grass gradually developed taller teeth that lasted longer, despite constant wear. Strong jaws and specialized digestive systems also became important for processing tough plant material. Open grasslands also encouraged faster movement. Animals living in these wide spaces needed to escape predators or chase prey across long distances. Longer legs became common among many grazing mammals. Hooves became more specialized. Strong muscles supported long-distance travel. Predators changed as well. Running became more important for catching prey in open country. Better eyesight allowed hunters to spot animals from greater distances. Endurance became valuable because chasing prey over long distances required efficient movement. Climate continued changing throughout the Miocene period. Some areas became drier, while others remained wet. Grasslands spread even farther. Forests survived in many tropical and temperate regions, but occupied less land than before in several parts of the world. Mammals kept adapting to this changing balance between forests and open environments. The ancestors of many modern grazing animals expanded during this time. Horses developed larger bodies, longer legs, and single hooves. Antelope, deer, giraffes, camels, and cattle relatives became increasingly diverse. Their digestive systems allowed them to process grasses and other plant material efficiently. Elephants also continued changing. Several different elephant relatives appeared, including forms with different tusk shapes and tooth patterns. Some lived in forests while others occupied grasslands. Climate determined where food plants grew, influencing the distribution of these giant herbivores. Marine mammals experienced important changes too. Whales became fully adapted to ocean life. Some developed baleen plates for filtering tiny animals from seawater. Others remained active hunters with large teeth for catching fish, squid, and marine mammals. Ocean temperatures and ocean currents influenced where food became abundant, leading whales to migrate across great distances. Seals, sea lions, and walruses also evolved from land mammals that gradually became adapted to marine life. They spent much of their time in water while still returning to land or ice for resting and breeding. Changing coastlines and ocean temperatures shaped their distribution. Climate also influenced the spread of primates. Warm tropical forests remained important homes for monkeys and apes. As forests changed, some primates adapted to more open woodland habitats. Different food sources encouraged different body sizes, social behavior, and movement. The ancestors of humans belong to this long primate history. Environmental changes in Africa affected forests and grasslands. Some populations spent more time moving across open ground between patches of woodland. Over millions of years, these changing environments influenced body structure, walking ability, diet, and behavior. During the later part of the Age of Mammals, Earth's climate continued becoming cooler overall, although warm and cool periods alternated many times. Ice sheets expanded and retreated repeatedly during the Ice Ages. These repeated climate changes strongly affected mammal populations around the world. Large ice sheets covered much of North America, Europe, and Asia during the coldest periods. Sea levels dropped because large amounts of water became locked inside ice. Land bridges appeared between regions that are now separated by water. Mammals crossed these temporary connections, spreading into new continents. One famous land bridge connected Asia and North America across the region now occupied by the Bering Strait. During colder periods, many mammals crossed this route in both directions. Mammoths, bison, wolves, bears, and early humans eventually moved between the continents. Cold climates favored mammals with thick fur, layers of body fat, and other features that reduced heat loss. Woolly mammoths developed long hair, curved tusks, and large bodies suited for cold environments. Woolly rhinoceroses also possessed thick coats that protected them during harsh winters. Other mammals survived by changing their behavior rather than developing major physical changes. Some migrated to warmer areas during cold seasons. Others hibernated, lowering their body activity to conserve energy when food became scarce. Many stored food before winter arrived. Burrows provided protection from freezing temperatures and strong winds. Smaller mammals often adapted more quickly because their populations reproduced faster. Mice, voles, rabbits, squirrels, and similar animals occupied countless habitats. Their flexibility allowed them to survive repeated environmental changes. Birds also benefited from changing climates, but mammals became especially successful because of their wide range of body sizes, diets, and behaviors. From tiny shrews weighing only a few grams to giant whales weighing many tons, mammals eventually occupied nearly every major environment on Earth. Deserts presented another challenge created partly by changing climate. As rainfall decreased in certain regions, deserts expanded. Mammals living there developed many ways to conserve water. Some became active mainly during the night when temperatures were cooler. Others stayed underground during the hottest part of the day. Specialized kidneys helped reduce water loss. Mountain regions created different conditions as elevation increased. Higher elevations usually brought cooler temperatures and thinner air. Mammals living there developed thick fur, efficient lungs, and blood systems capable of carrying oxygen effectively. Goats, sheep, yaks, and many rodents became well adapted to mountainous environments. Rainforests continued serving as important centers of mammal diversity. Dense vegetation provided countless food sources and hiding places. Tree-dwelling mammals developed gripping hands, climbing claws, long tails for balance in many species, and excellent vision suited for life among branches. Wetlands supported beavers, otters, muskrats, and many other mammals. Rivers and lakes supplied water throughout changing seasons. Aquatic plants, fish, insects, and shellfish provided abundant food. Arctic regions supported mammals able to survive freezing temperatures for most of the year. Polar bears, Arctic foxes, musk oxen, seals, and several whale species became closely linked to ice-covered environments. Seasonal ice influenced feeding, breeding, and migration. Throughout all these changing climates, natural selection continued shaping mammal populations. Individuals possessing traits that improved survival under local conditions often produced more offspring. Over many generations, helpful characteristics became more common. Small differences accumulated slowly, eventually producing entirely new species. The Ice Age world of early humans was shaped by long periods of cold weather that changed the land, the plants, the animals, and the lives of the earliest human groups. These cold periods did not happen only once. They returned many times over a very long part of Earth's history. Between the cold periods, the climate became warmer for many thousands of years before another cold period arrived. These repeating changes affected where people could live, what food they could find, how they traveled, and how they slowly developed new skills that helped them survive. Early humans lived through changing weather that lasted much longer than a single lifetime. Each generation inherited a world that continued to change as the climate shifted. The Ice Age was not a single period when every part of Earth was covered with ice. Large ice sheets spread across wide areas of the northern part of the world, especially across much of North America, Northern Europe, and Northern Asia. At the same time, many other places remained free from permanent ice. Some areas had cold grasslands, open forests, or dry plains instead of thick glaciers. People and animals continued to live in these places by finding ways to adjust to the changing seasons and changing weather. The first human ancestors had already appeared long before the most recent Ice Age, reached its greatest size. Earlier human species had spent millions of years adapting to different environments in Africa, before later human groups spread into other parts of the world. During these long stretches of time, the climate in Africa also changed many times. Wet periods brought larger lakes, rivers, and greener land. Dry periods caused grasslands to spread while some forests became smaller. These repeated changes encouraged early humans to become more flexible in the way they found food and moved across the land. Climate changes happened because of several natural processes that worked over very long periods. Small changes in Earth's movement around the Sun affected how much sunlight reached different parts of the planet during different seasons. Changes in the shape of Earth's path around the Sun, the angle of Earth's tilt, and the direction of Earth's axis slowly changed the amount of heat that reached the surface. These slow changes influenced the growth and melting of large ice sheets. Volcanoes, ocean currents, and changes in the atmosphere also played important parts in shaping the climate. As the climate became colder, snow that fell during winter often remained on the ground instead of melting completely during summer. Over many thousands of years, fresh snow continued to pile on top of older snow. The weight of these layers slowly pressed the snow into thick ice. These growing ice sheets spread across huge areas of land. In some places the ice became several kilometers thick. The enormous weight of the ice pushed down on the land beneath it. When the ice later melted, the land slowly began rising again, a process that continues in some places today. Glaciers slowly moved across the land under their own weight. Even though they often moved only a short distance each year, they continued moving for thousands of years. As they advanced, they scraped rocks, carried soil, and changed the shape of hills and valleys. They left behind lakes, smooth rock surfaces, piles of stones, and new river paths. Many natural features seen today were formed during these long periods of moving ice. The colder climate affected the amount of water in the oceans. Much of Earth's water became locked inside the growing ice sheets. As a result, sea levels became much lower than they are today. Land that is now covered by shallow seas became dry ground. These land bridges connected regions that are now separated by water. Animals and early humans used these connections to move into new places. When the climate became warmer again and the ice melted, sea levels rose and covered these land bridges. One of the most important land bridges connected northeastern Asia with northwestern North America. This wide area of dry land existed because sea levels were much lower during colder times. Groups of animals crossed this region over many generations. Later, groups of humans also traveled across it, slowly entering North America. Their movement did not happen during a single journey. Families and communities gradually spread over many generations as they searched for food, water, and safer places to live. Changing weather affected the plants that grew in different places. During colder periods, forests became smaller in many regions, while open grasslands spread across large areas. Cold-resistant plants survived where temperatures remained low. During warmer periods, forests expanded again as trees returned to areas where they had disappeared during colder times. These changing plant communities affected every animal that depended on them for food and shelter. Animals also responded to the changing climate. Large grazing animals spread across the cold grasslands because they found enough plants to eat. Herds of mammoths, woolly rhinoceroses, bison, wild horses, reindeer, musk oxen, and other animals moved across wide open spaces. Predators followed these herds. Wolves, cave lions, hyenas, bears, and other meat-eating animals depended on these plant-eating animals for survival. Early humans became part of these natural systems by hunting some animals and gathering many kinds of wild plants. The animals that lived during the Ice Age often had features that helped them survive in cold conditions. Many developed thick fur that trapped warm air close to their bodies. Some stored layers of fat beneath their skin to reduce heat loss. Others had shorter ears or tails that reduced the amount of body heat escaping into the cold air. Different animals survived in different ways, depending on where they lived and the food they needed. Early humans also faced the challenge of staying warm during cold weather. They learned to use animal skins as clothing. Instead of wearing simple coverings, they gradually created fitted garments that covered more of the body. They used sharp stone tools to cut hides and remove unwanted material. Later, they made bone needles that allowed them to sew pieces of skin together more carefully. Well-made clothing helped reduce the danger of freezing temperatures, especially during long winters. Shelter became increasingly important as the climate changed. Early humans often used natural caves when they were available. Caves provided protection from cold winds, snow, rain, and dangerous animals. Not every group had access to caves, so many people built temporary shelters using wood, branches, animal bones, hides, and other natural materials. Some shelters were rebuilt many times as families returned to the same hunting areas during different seasons. Fire played an important part in daily life. Controlled fire gave warmth during cold nights and helped people survive harsh winters. Fire also provided light after sunset and allowed food to be cooked. Cooked food was often easier to chew and digest. Fire helped dry wet clothing, harden wooden tools, and keep dangerous animals away from camps. People gathered wood whenever possible, although finding enough fuel during cold periods could be difficult in places where trees were scarce. Stone tools became more advanced as human knowledge increased over many thousands of years. Early stone tools were simple, but later tools became more carefully shaped for different purposes. Some were made for cutting meat. Others were designed for scraping animal hides, shaping wood, digging roots, or preparing plant foods. Spears became more effective for hunting large animals. Stone points were carefully attached to wooden shafts using natural materials such as plant fibers, tree resin, or animal sinew. Knowledge about making tools was passed from one generation to another. Children learned by watching older family members work with stone, wood, bone, and antler. This sharing of knowledge allowed useful ideas to survive even when weather conditions became difficult. Small improvements in tools often increased the chances of finding food or protecting families from danger. Early humans rarely stayed in one place throughout the entire year. Many groups moved with the changing seasons because food supplies changed from one season to another. During warmer months, they might hunt in one area where animals gathered. During colder months, they might move to another place with better shelter or more reliable food sources. These seasonal movements became part of everyday life for many generations. Food sources changed throughout the year. Hunting provided meat, fat, bones, hides, and other useful materials. Gathering remained equally important. People collected fruits, berries, seeds, nuts, edible leaves, roots, mushrooms, and many other natural foods whenever they were available. Fishing also became important in many places where rivers, lakes, and coastal waters provided fish and shellfish. No single food source was always available. Weather affected the growth of plants, the movement of animals, and the condition of rivers and lakes. Successful groups adapted by using many different food sources instead of depending on only one. This flexibility increased the chances of survival during difficult years. Large animals often supplied much more than food. Animal skins became clothing and blankets. Bones were shaped into tools, needles, fishhooks, and spear points. Antlers served as useful raw materials for making strong tools. Animal fat provided fuel for simple lamps and added valuable energy to meals during cold weather. Sinew from animals became strong thread for sewing clothing and attaching stone points to wooden handles. Human communities depended on cooperation. Hunting large animals usually required careful planning and teamwork. People worked together to track animals, prepare hunting equipment, and share the food that was obtained. Older members of the group shared experience gained over many years. Younger members contributed energy and helped gather food, carry supplies, and care for children. Life during the Ice Age involved many dangers beyond cold weather. Strong storms could make travel difficult. Heavy snowfall sometimes covered important food sources. Rivers could freeze during winter and flood during warmer seasons. Dangerous animals shared the same hunting grounds. Injuries from hunting or accidents could become serious because medical knowledge remained limited. Illness also affected early human groups, especially when food became scarce or harsh. Weather weakened people over long periods. The size of early human groups often remained fairly small. Smaller groups could move more easily when food became difficult to find. Families stayed connected through shared work and shared responsibility. People depended on one another for protection, childcare, food gathering, hunting, tool-making, and shelter building. Cooperation became an important part of survival because no single person possessed every skill needed for daily life in changing environments. The repeated return of colder and warmer climates meant that people constantly adjusted their routines. Areas that supported large populations during warmer times sometimes became difficult to live in when temperatures fell. At other times, regions that had once been too cold became more suitable as the climate warmed. Human movement across different landscapes reflected these long-term environmental changes, rather than sudden travel over short periods.